Junath for getting my internet to work. So these are the results for algorithms. Okay? By the way, now that I have this thing working, on the left is the who to follow box. That the last time I was affiliated with Twitter was using the money algorithm. Now I'm sure they do other things. And you can look and see how strange these results are. The top 15 machine learning algorithms ranked, some cryptography, some gobbledygook, Apple how to shoot, Trump, cooking high, text analytics. But let's look at the people that I'm following. So because I have a good network on Twitter which is well curated. I'm following a lot of people who do serious algorithms. So the way you would use personalized PageRank, I realize it may not have been obvious what I was talking about in terms of search. You take all these results, you could do something as simple as just look at the people who made these tweets, and you could re-rank these tweets, the top 50 tweets or the top 100 tweets, just by personalized PageRank from me. And the results would improve dramatically. So there are definitely people here that I follow. So for example, Ryan Williams. Let me show this guy, Ryan Williams. He tweets. So this is what I would have loved to see. Or some other Ryan Williams. I can't even find the right Ryan Williams. Like, it's strange. This is a guy that I'm following, and he's a very well-known theoretical computer scientist. If I'm not following him, I'm following dozens of people that I'm following. And he's not showing up. His tweets are not showing up. There's another person that I follow. Right? So I would have loved to see things like this. Both VLDB and ACL via TACL have successfully decoupled publication from conference attendance. So it's a search engine. You would expect it to take algorithms, expand out the keywords. From algorithms also expand to theoretical computer science, get 100 tweets, and just re-rank them by personalized PageRank or something, and the results would improve dramatically. The results are now currently very generic. And
isn't there any other objective as to why they are showing this? And are you?
So why were they showing those results?
Yeah, there might be some other objective they have.
So they're doing some version of recency versus they're doing some version of recency versus.
Maybe some kind of profit maximization for them because.
No, because this person is not paying them,
No,
and this is not that recent a tweet. So this is probably just by global PageRank or anything by global importance. And so from a global importance point of view, this tweet might be very interesting to a lot of people who search for algorithms. It's just not that interesting to me. And so if they could personalize it somehow, I think it'll be much better. Yeah. So we could search for the other speaker and see what comes up. Yeah? It knows who I follow. So at the very least, it could do a personalized PageRank from me. Some intra-Twitter information. No. I mean, so every company pretty much knows everything. And the reason is because whenever you go to a page now, anything which is selling anything, there'll be a link at the bottom saying tweet this or like this. And those buttons are actually pixels or cookies. So anytime you go to a web page which has tweet this or Facebook that or like this or link this or pin this, a cookie gets generated. And so any page that I've ever been to which has a Twitter tweet this button, Twitter knows I've been there. And because I also go to Twitter, they can join the cookies and they essentially know everything. And so, but that is a complex process. At the very least, they should be able to use my Twitter network to personalize results for me. Right? And so that's what gets my goat more than anything else, that they're not even using my network to personalize things for me. Right? And it's not just Twitter. I can do this kind of search on pretty much any place. I can do it on Google. And I can search for someone on Google, and you'll see that the results are not personalized to even my Google Plus network.
But they add
not to my network. So they often, so the ads might be personalized to my network a little bit too, yeah.
So my assumption was that maybe they're trying to optimize something.
No, the ads are personalized, but this is not an ad.
Yeah, take
Yeah,
it off.
yeah. Yeah, but I mean, they do a lot of things for which there's no monetary incentive. I think one of the reasons is that this problem is I do think one of the reasons is that this personalized PageRank queries are very hard. So I think like this is, I do think, so for example, since one of the goals here is to look for hard problems that someone might do research on, I feel like doing personalized search, personalized to your network is a genuinely hard problem. And so people haven't just solved the technical problem. So the question is, what's hard about personalized PageRank as opposed to general PageRank? As opposed to say general PageRank or general ranking. Nothing is harder about personalized PageRank compared to general PageRank. It's the same problem. The question is, what's the difference between targeted advertising and general personalized PageRank? First of all, advertising tends to be more interest-based than network-based. That's one difference. And the other difference is the number of advertisers is small. And because the number of advertisers is small, you can do things which are starting from the advertisers. You can grow, for each advertiser pays a lot of attention to deciding, to sort of describing who they want to target to. And the number of advertisers is small, so it's easy to expand out from them. The number of all tweets is much larger, so it's hard to personalize results to do it for all tweets. And there's nothing harder about personalized PageRank compared to general PageRank, except a general PageRank you would need to compute only once. Personalized PageRank you need to do it from everybody. And maybe I should also point out, I might have said something which sounds contradictory. In the last lecture, yesterday I described personalized PageRank for recommendations, right? And I said that Twitter does it. It does it routinely. At least it used to do it routinely. And I didn't suggest that it's a very computationally hard problem, even though it was using personalized PageRank. Today I'm saying that personalized PageRank is so hard that companies are not really doing it. Is it obvious what the distinction is? Maybe I should clarify the distinction. Yeah. When you're using personalized PageRank for recommendations, we're looking for head queries. So yesterday when I was doing personalized PageRank for recommendations, we had this collaborative filter. I would start from a node C. I would do some kind of a personalized PageRank in this consumer producer graph. I could do it using Monte Carlo. And then the goal was to find the top results, the ones which have the highest personalized PageRank, and so give them to me as recommendations. So looking for head queries. So you could imagine setting the delta, the threshold beyond which you want to find. You could imagine setting a delta to be like 1 over 10,000, for example, right? And that's the regime in which recommendations operate. Today I'm talking about doing personalized PageRank for search. Search tends to be in tail queries. When I search for algorithms, I get these results. Those results are not going to be among my top 10 personalized PageRank nodes. They're going to be somewhere deep in the personalized PageRank spectrum. So I'm looking for delta, which is going to be like 1 over 10 to the power 7 or 10 to the power 8. So re-ranking search results using personalized PageRank, even though it might sound structurally similar, is a very different problem from generating recommendations using personalized PageRank. Okay. In one case, you're looking for the head. In other case, you're given some tail results and you need to re-rank them. Because I did a search for something, I'm going to get results. My head results would be like Obama, Trump, IISc, IIT Bombay. When I search for algorithms, and especially on a place like Twitter, I'm really interested in only what people said recently about algorithms. So maybe none of the people in my head, maybe Obama didn't say anything about algorithms today. He might have something about algorithms last year, but not today. So the results that I'm trying to re-rank are going to be people who are very deep in the PageRank spectrum. And so the flavor of the problem changes quite dramatically. In recommendations, I'm just looking for the top few results in personalized page rank, which is very easy to find using Monte Carlo. That's basically what Monte Carlo is meant for, finding like these heavy hitters very quickly. Whereas for algorithms, I'm given these 100 results. I'm given the 100 most recent tweets, which have the word algorithms. I want to re-rank them. These are like completely arbitrary tweets, and re-ranking them could be a very hard problem by personalized page rank. So I think this problem is sort of genuinely technically difficult. And so I think that's at least one part of why companies don't do personalization based on your network. Companies do a lot of personalization based on your interests, based on your demographics, based on your geography, but not based on your social network. No, so you definitely need recency. So the question is, can you not do things based on recency? You definitely need recency. But I feel like in addition to recency, you also need personalization. I'm not interested just in the most recent 100 tweets about algorithms. I'm interested in the most recent 100 tweets about algorithms that have something to do with me, or that conceivably have something to do with me. And those tweets are not going to be very high on the personalized page rank spectrum for me, so re-ranking them is a much harder problem. So I think because the audience is a little bit diverse, I feel like part of what I need to do is, instead of going deeper and deeper into a topic, so this issue of social search is very dear to my heart, and I have like more material that I could cover. Instead of going deeper into it, I want to give you like a flavor of something completely different, which also has nice conceptual properties which relates to this material. And so that thing is going to be credit networks. So credit network is sort of, we're going to change tracks completely. There are still going to be random walks, but these random walks are going to be very different in these credit networks than anything we have seen so far. So credit network is a decentralized payment infrastructure. It was introduced initially independently by DeFigurado and Barr in Davis, and Ghosh et al. From Yahoo. And it's a model of a currency model which does not need banks or common currency. And it models trust in network interactions. And you can think of it as a robust reputation system for transaction-oriented social networks. And I'll give a concrete example. So one concrete example is that there's a cryptocurrency called Stellar. It's one of the 10 best, most used cryptocurrencies. And the way it works is that they have these anchors in every country. And you can use an anchor to sort of make payments in any currency via your anchor to another anchor. So it's like a cryptocurrency with just some connections to the real world. And these anchors, if there's an anchor in Ireland which is talking to an anchor in Taiwan and they're sending money to each other, they don't immediately send money. They wait to see, maybe some money is going to come back. And so there are some limits, and they say, well, within this limit, the anchor in Ireland is going to trust the bank in Taiwan and not insist on immediately receiving payment. And if by some chance a reverse transaction comes through, then you never had to send actual money across, and that reduces transaction costs dramatically. So that's the kind of thing that's a motivation for what we are doing here. So once again, in most problems in social algorithms, you tend to start not from a computational model, but some kind of a socio-economic system. If we want to understand distributed currencies, then we start from like what a currency is. Okay? So I mean, of course, one currency is barter. If I need a goat from you, I'd better have the blanket that you're looking for, right? Otherwise, I can't trade. And so that is very low liquidity, because I might want a goat and I have a blanket, but I can't do the trade because there's nobody else who wants that blanket. Yeah. And so centralized banks take care of this by issuing currencies, and all modern currencies are essentially IOUs, right? And some are explicitly IOUs, and like for example, the rupee is like explicitly has this thing which says I promise to pay the bearer the sum of 100 rupees. So it's very explicitly an IOU. And some currencies like the US dollar are like not explicitly IOUs, but they are they don't explicitly say they're an IOU, but in reality they are. And so they're very high liquidity and they allow strangers to trade freely. Okay? That's the advantage of these centralized currencies. And credit networks as proposed by De Figueiredo and Barr and Ghosh et al. Are like centralized currencies in the sense that they are IOUs, but they're also like barter in the sense that they're bilateral. You're bilaterally exchanging these IOUs, and you're only doing it among friends. Okay? And so here's what this currency looks like. Okay? So let's say there's this guy, yes, Obelix, yes. This guy Obelix, and he needs $10 worth of stuff. Yeah? So in a centralized currency, he just gives $10 to Asterix. And what's really happening there, actually let me split this. Let me skip this for a second. Yeah. And so in a credit network, what would happen is that instead of Obelix paying Asterix $10, Asterix says, Obelix, I trust you for 10 IOUs. And what that means is what Asterix is saying is that Obelix, I'm willing to accept 10 IOUs from you without any collateral. More than that, I'm not willing to trust you. So if Obelix needs $10 worth of stuff from Asterix, what it's going to do? And so Asterix might say, okay, Obelix might say, I trust you for 90 IOUs. And these trust relations we're going to model as edges in this network with capacities. Okay. So now if Obelix needs 10 IOUs worth of stuff, he's not going to use dollars, he's going to use his own currency. So this picture is not rendering very well, but those small rectangular things, those are like, think of them as dollars signed by Obelix instead of by the Treasury Secretary in the United States. Okay. So he prints these dollars and he gives these dollars to Asterix. Okay. And Asterix is going to give him some service. So as a result of this, how many more IOUs does Asterix trust Obelix for now? 0. Next time Asterix needs something from Obelix, what should Asterix do? Asterix will first pay Obelix back using Obelix's IOUs. Why would I hold, if I need something from you and I have an IOU from you, I'll first give you that IOU and only then will I give you anything else. Okay. But even after Asterix gives those 10 IOUs to Obelix, Obelix still trusts Asterix for 90. So what really happened here as a result of Obelix giving these 10 IOUs to Asterix is that Asterix trust in Obelix went down by 10 and essentially Obelix trust in Asterix went up by 10. Okay. So you get these new trust values. The top edge became 0, so it disappeared, the bottom edge became 100. Okay. And you can completely forget about the fact that Obelix gave Asterix 10 IOUs. That fact is gone. All the information about the new state of the network is encoded in these new trust values. You don't have to remember the entire history of how much Obelix gave Asterix and how much Asterix gave Obelix. Okay. And so, does this make sense? So at any given time, the only thing that's relevant is the trust edges and the capacity on these trust edges, and not the history of how you got there, who gave how many IOUs. So you can completely forget about IOUs and just remember these trust values. Yeah. So you can do the same thing at a distance. So imagine that there's this bard and there's this ironmonger, fully automatics, and the bar doesn't, these are trust values, and so as you know, the fully automatics and cacophonics don't really like each other, or in fact, fully automatics doesn't like cacophonics. Cacophonics sort of indifferent, and so there's no trust value from fully automatics back to cacophonics. Okay? Or sorry, there's no trust value from. There's no direct relation between cacophonics and fully automatics. So they're connected by other people. So this guy fully automatics, the ironmonger, needs a favor from cacophonics, which is the bard. Okay? So what you can do is, even though cacophonics doesn't trust fully automatics directly, fully automatics can give one fully automatics dollar to Asterix because Asterix trusts him. Asterix can give one Asterix dollar to Obelix, and Obelix can give one obelix dollar to cacophonics. And as a result, the trust value from asterisk to fully automatics goes down by 1, from obelix to asterisk goes down by 1, from cacophonics to obelix goes down by 1, and the reverse direction it increases by 1. Okay. And so you get these new trust values. Okay. And you can again forget who gave someone how many IOUs. So exactly the same idea works at a distance. And for those of you who have seen network flows before, this is exactly equivalent to doing an augmentation of a single commodity flow. Okay. So even though you're doing these bilateral exchanges and these trust relationships are bilateral, and the whole idea of this was like, I trust you, I'm not trusting a random person. Even so, the process that actually happened was equivalent to doing, if you follow this process back, it was equivalent to doing an augmentation of a single commodity flow from the recipient to the buyer. Okay. So you add a capacity of 1 in the reverse direction, you delete a capacity of 1 in the forward direction. Okay. So repeatedly doing these single commodity augmentations. Okay. And so what's a credit network is basically there's a graph G, V, comma E with capacities which represents a network. It could be a social network, a P2P network, whatever, right? And nodes are non-rational agents / pairs who print their own currency. By non-rational, I mean like something very specific. I'm going to assume that these nodes do what we tell them to do. They're not nodes these are nodes who are just declaring how much they trust each other, and they're declaring them truthfully. They're not trying to sort of be strategic, saying, okay, if I say I trust that guy, it's going to benefit me more than by saying that I trust this guy. So by non-rational, I mean they're non-strategic. There's these edges, and so edges are going to be, you can think of edges as credit them as CUV bigger than 0 extended by nodes to each other. I'm assuming that all currencies exchange rates are 1. I'm not going to worry about exchange rates. They don't matter in this network, but I'm not going to worry about them. And payments are made by passing IOUs along a chain of trust, and this is the same as the augmentation of a single commodity flow along a path from payee to payer. Okay. So this is, I think, the most important part, that even though this network, these are bilateral IOUs, this is equivalent to doing a single commodity augmentation. And credit gets replenished when payments are made in the other direction. Okay. Because you can imagine that I want something from you, then you want something from me, and you can imagine that this credit gets replenished when a reverse augmentation happens. Okay. And so this has some very nice robustness properties, which is why it got proposed. Okay. Every node is vulnerable to default only from its own neighbors and only for the amount it directly trusts them for. Okay. And this kind of statement is typical in social algorithms. Instead of having some kind of a computational guarantee, you have a guarantee which is about socio-economic behavior of the system. So let's say I trust Professor Manjunath directly, and so he gives me 10 IOUs. I do something for him, and then he runs away. Okay. Then I am the only one who loses. Okay. If somebody else trusted him because of me and they went through me, then as long as I am there, they don't care that he ran away and they are holding IOUs, they did some service for him. Okay. So every node is vulnerable to default only from its own neighbors and only for the amount it directly trusts them for. So there's a strong robustness guarantee. Okay. That's why these networks that's why I think these networks are very interesting. Okay. So if the anchor at Ireland trusts the anchor in Taiwan, in the example that I gave, if the anchor in Taiwan goes away, it's only the anchor at Ireland that's left holding the bag. As long as the anchor in Ireland doesn't go bankrupt, nobody else is exposed. So the examples are there. You can use them for barter such exchange economies like peer-to-peer networks. So you can use something like this, for example, in BitTorrent to keep track of who owes someone how much in terms of how much they uploaded or downloaded. You can use it for ensuring transactions in peer-to-peer commerce such as Craigslist, for combating social spam, email spam, question and answer systems. So so Quora, for example, has a credit system which is sort of roughly modeled after this. Not exactly, because they don't have personalization, but sort of Quora has a credit system for answering questions which is somewhat like this. And there's a cryptocurrency called Ripple which has its roots in credit networks. So you could imagine that So there's a system out of Rice made by Peter Druschel. It's an experimental system. They ran it on the Rice network, which was basically a credit network that they ran. Not inspired by our work, but the original work by the people in Yahoo and DeFicado and Barr. And what they did was each time they sent, so the question is how can you use this for combating spam? And so what happened in the system is each time you get an email, the sender of the email has to give you $1, a virtual dollar in this scenario. If you directly trust them, then there's no issue. If you don't directly trust them, there has to be a trust path between them and you. And so what they did was they inferred initial trust values based on, they looked at who's sending emails to who and who's responding to whose emails, and they used to establish this initial trust network. And then if you read someone's email, then that dollar goes back to them. So they made this network and they assigned monetary values to how much it costs to send an email, to receive an email, to respond to an email. And they injected enough credit in the system that regular people could transact freely by sending emails back and forth, but spammers, because they're not receiving any payments from anybody else, nobody's reading their emails, nobody's liking their emails, responding to emails, they would run out of this, this currency. Okay. And so for an application like that, it's important for the system to have liquidity, in the sense that if you're doing regular operations, you shouldn't run out of trust. You should be able to keep doing these transactions. But people who are just only buying will run out of currency to buy with. So liquidity is, so there are two research questions. One of them I'm going to touch upon today, the other one I'm going to leave aside. The first is liquidity, which is, can credit networks sustain transactions for a long time, or does every node quickly get isolated, so there's going to be no transaction? And the second thing is network formation, where if you assume these nodes are rational and strategic, how do they decide how much trust to assign to each other? Okay. So like I said, I'm going to focus on the first question. I'm going to leave aside the question of how I decide how much to trust you. We just assume that these trust values are given to us exogenously, and people just report them truthfully. And I'm not going to worry about where they come from. Yeah. Yeah, so the question is, why are these intermediate nodes participating? Or are they participating freely? Yes, they're participating freely. And we are assuming that, so that's part of assuming that they're non-strategic. So you could imagine a situation where a node is very strategic and says, I'm going to do Professor Arbange's transaction, but not Ashish's transactions. So we're going to assume that none of this happens. So I'm going to assume that the model I described before is the model that actually happens. Intermediate nodes participate, there are no transaction fees, and people have just declared their trust values. Okay. And the strategic issues become very interesting in and of itself. Okay. So in the liquidity model, I'm going to assume that edges have integer capacities. Yes? Western Union, yeah. Yeah. No, not really, because not as far as I know. They are very efficient payment systems because they're very efficient ACH. But they don't, because I think Western Union is normally often used for sending money back from one place to another, so they tend to have these very strong directionality to it. Because I think there's a lot of money, there will be a lot of money flowing, say, from US to Mexico, but not that much flowing from Mexico to the US. They would definitely do it, yeah. They would definitely clear whatever they can internally. But somehow, for some reason, something like this, this would be a very natural thing to do, for example, at PayPal, where instead of paying you, I could say, well, you could say you trust me for this money and not actually do the clearing. So you could imagine that this would happen more often, but surprisingly, it hasn't really taken off. So the question is the goal to look at more complex networks like a star network? Yes. So a centralized currency is a star network. So let me actually make that point more explicitly. Okay. By going back to this original example that I had. Okay. So in the case where Obelix is paying asterisk $10, right? You can model even that situation with a centralized bank as a credit network. So what's really happening here is if Obelix has $10 in his pocket, we can model that as saying that the central authority, let's say the Federal Reserve Bank of the United States, trusts Obelix for 10. So that's the same as Obelix having 10 IOUs in his pocket, $10 in his pocket is the same as the central bank saying that I trust you for 10. Okay. And maybe Asterisk has $90 in his pocket, so it's the same as saying that the central bank trusts Asterisk for 90. No, because I have the IOU. So when I have the IOU, I can give it to you. So it's as if you trust me for 10. Yeah. And basically, because of the Federal Reserve, you can think of Obelix and Asterisk trusting the Federal Reserve for infinite amounts. If I have, so the question was if, yeah. So if you have my IOUs for that, because what we are modeling with this trust is the fact that you can come to me and demand something. So the question is, can you claim that? Can you say that I have the IOU, but I'm not going to give it to you? Not if you're an intermediate node. If you're an intermediate node, you have to be willing to clear transactions. If you're an end node, then of course you're free to say, well, I don't want to sell you something, or I don't want to buy something from you. So intermediate nodes have no agency here. And so these edges, these infinite edges from Asterisk to Obelix, represent the fact that Asterisk and Obelix trust the Federal Reserve for essentially infinite amounts. For example, if the Federal Bank of the US wants to give me money, I'll keep taking it. If they give me more than $5 trillion, then I'll ask them, are you good for more than $5 trillion? But that's like essentially infinite, right? So up to $5 trillion, I'm going to take US dollars without like any questions. So the reverse edge of infinite essentially means that Asterisk and Obelix are willing to trust the Federal Reserve for arbitrary amounts, which essentially means they're willing to be paid any amount in US dollars. Okay? So you can essentially model the centralized network also as a distributed currency, as a credit network. And so I think Himanshu's question was, are we interested in more complex networks than stars? And yes, because a star is basically a centralized currency. This is a star network. You could have many participants. No, I don't. So the question is the Western Union more of a star network? No, the Western Union is not more of a star network, because nobody is really trusting the Western Union. So I'm not holding any IOU from the Western Union. The IOU that I'm holding is still from the Federal Reserve. An IOU from the Western Union would be something that's only good at the Western Union and not somewhere else. So I'm going to assume that edges have integer capacity, just C bigger than 0. Summing up, I'm going to sum up both directions, ignore the direction of the trust. It's not going to matter what direction the trust is in, as we'll see later. I'm going to assume that the transaction rate matrix lambda, and so which is lambda UV, and so lambda UV is the rate at which U wants to send $1 to V, okay? Or U wants to buy something from V. Okay? So it's a standard rate matrix. Okay? I'm going to assume that this rate matrix is symmetric. That's essentially all. It's symmetric and connected. That's all I'm going to assume. Okay? And if symmetric and connected doesn't immediately mean something to you, then you can just assume the lambda UVs are all the same. Okay? I'm going to assume that repeated transactions at each time step, you're going to choose the source of the transaction, and the destination of the transaction is probably lambda ST. So that's what it means for it to be a rate matrix. And then we're trying to route a unit payment from S to T by the shortest feasible path. Okay? And we're going to update edge capacities along the path, because like I said, this is just like an augmentation, and we'll repeat. And we'll say a transaction fails if no path exists. And liquidity is basically what fraction of the transactions succeed, and non-liquidity is what fraction of the transactions fail. Okay? So does that make sense? So far the model was very general, but to analyze liquidity, I need to have some very specific model of transactions, and this is my transaction model. Okay? So to analyze this, it seems like a very hard thing to analyze. And the reason it's hard to analyze is because these transactions are going to create a Markov chain, right? Because each time this transaction arrives, you change the state. But the state of the system is the entire network. right? So when you do this Markov chain, you're moving from state to state, you're moving from state to state, but the state is the entire network with all its capacities. So simplify this, we're going to first define this thing called cycle reachability. So let S and S prime be two states of the network. We say that S prime is cycle reachable from S if the network can be transformed from state S to state S prime by routing a sequence of payments along feasible cycles. So if you look at the left-hand network, if I send a transaction, if I send $1 from U to Y, Y to W, W to V, and V to U, then all the forward capacities are going to 0, all the reverse capacities are going to become 1, and I'll get this other network. Okay? And so I'll say the second credit network is cycle reachable from the first credit network. Okay? So this is going to be like the most crucial part of this analysis. So if it's not clear, please do interrupt me. Oh, so the motivation is that even though I'm carrying around this state of the network, a lot of this state is actually unnecessary. Because anything that, if I can send flow along a cycle, then I can also unsend it along the cycle. And so basically, I'm going to move from state to state in this Markov chain, but a lot of the information that I'm carrying out is unnecessary. So maybe by eliminating this unnecessary information, maybe my Markov chain will become simpler. So in fact, that's exactly what's going to happen. So the question was, why am I defining this? So what's going to happen is instead of thinking of the state of the network as the credit network, I'm going to think of this. I'm going to take all the states of the credit network which are cycle reachable and collapse them into one equivalence class. And I'm going to analyze the Markov chain on these equivalence classes. Yeah. 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 So the question is, should we interpret like a settlement that's already happened? Yeah, you could interpret that as that, or you could say that you can do a null settlement. You can do a settlement where nobody receives anything, nobody gives anything, because you just send flow to a cycle. So in this case, you can think of U paying itself. So U paid itself, so nothing actually changed, no actual real transaction happened, but you change the state of the network. So if you can change the state of the network without doing any actual payment, because U paid itself via some path, then you will say that these two states are cycle reachable. So there's a theorem which is also a motivation. So let's say there's a sequence of transactions which succeed when the payment is routed along the shortest feasible path from SI to TI, always. Okay. Then the same set of transactions succeed when the payment is routed along any feasible path from SI to TI. So basically what that means is that the path along which you send payment is not really that important. And the reason is, if I send a unit of flow along two different paths on the same source or the same destination, you lead to states that are cycle reachable. So if I were to send flow along like this, send a unit of flow like this, versus I send a unit of flow like that. Here I might get one state. The state that I get from here might look like this. The state that I get here might look like this. These two states are going to be cycle reachable, so it's not going to really matter which route I use. So basically, even though it sounds like routing was an important part of this problem, if I want to send something from SI to TI, I have to choose a path. As long as it's a path, it doesn't matter which path you choose, because you're going to get into if you choose this path versus that path, you'll get into cycle reachable states. So it's not going to matter. Because from one cycle reachable state, you can go to another by sending null payments. So basically, cycle reachability partitions. So that's the motivation for cycle reachability. It partitions all possible states of the credit network into equivalence classes. If two things are cycle reachable, then they're in the same equivalence class. And then we prove this theorem that if the transaction rates are symmetric, then the network has a uniform steady state distribution over all reachable equivalence classes. So instead of doing a Markov chain, now you have to just do counting of these equivalence classes. And the intuition is the following. So let's say I have an equivalence class C here, and I have another equivalence class C prime here. Okay? And let's say I send flow, I get a transaction from S to T, which sends me from this equivalence class to that equivalence class. Then the reverse transaction from T to S will send me from that equivalence class to this equivalence class. And so, which means that the transition rate from C to C prime is the same as the transition rate from C prime to C, and that's enough to prove that the stationary distribution is uniform over all these equivalence classes. So if I want to find out what's the success probability in a particular network, I just look at all its equivalence classes, and I find out in which of these equivalence classes could I go from S to T, and that will give me the overall success probability from S to T. Yeah, so I assume that lambda ST equal to lambda TS. Yeah. So in the model, I didn't assume that they're symmetric. So that assumption is here. So the transition is symmetric. I'm just assuming that lambda ST equal to lambda TS. Yeah. All transactions are unit value. Oh, so that was your question. So the question was, are all transactions unit value? Yes. I'm assuming all transactions unit value. So again, the model is very general, but this analysis is specific. The analysis applies to the case of unit transactions and when the transaction rates are symmetric. Okay? So as a consequence, this immediately leads to complete characterization of success probabilities in trees, cycles, or complete graphs. In trees, there's only one path, so any class is an equivalence class and it becomes easy to analyze. We get good estimates for Ardor-Shenny graphs, and I'm going to point out some beautiful connections to standard graph theoretic problems at the end. So here's a very simple example. You assume a two-node network. You assume capacity C. Then we have C plus 1 states, each in a different equivalence class. If your total capacity is C, then you could have, and you have just two nodes A and B, you could have all the capacity going from A to B, or you could have C minus 1 going from A to B and 1 going from B to A, and then all the way down to 0. Okay. Each of these is an equivalence class. Each of these is equally likely because each equivalence class is equally likely. The only time you can't do a transaction from A to B is when B doesn't trust A at all. So only one of these leads to failure. So in a two-node network with capacity C, your success probability is C over C plus 1. Now, of course, this is not a big result. You could have derived it directly.
Capacity of the network or capacity of an edge?
Of an edge. Yeah, because a two-node network, we assume Kevin. So for example, you can do the same thing in a tree. There are no cycles, hence all states are equally likely. So if C1, C2, Cn are the capacities along a path from S to T in the tree, the success probability is the product of the Ci over Ci plus 1 along the path in the tree. You can also examine, you can use the same thing to examine bankruptcy probabilities general graphs, right? So I can show that, again, I'm not going to prove this, assuming that capacity C equal to 1 on each edge, and assuming the Markov chain is ergodic. It's a slightly weaker assumption than I made before. Earlier I said the transition is symmetric, everything is reachable, and so that automatically means Markov chain is ergodic. In reality, it needs something weaker. If that doesn't make sense to you, please ignore it and just assume we are in the previous model. Let dV denote the degree of node V, then the stationary probability that V is bankrupt is at most 1 over 1 plus dV. And we'll say a node is bankrupt, but nobody trusts that node. Yes? No, so I think I was careful to say over all reachable equivalence classes. So there's an equivalence class that you can't reach because maybe the network was already disconnected, then it won't work out. Yeah, yeah, thank you. But in general, I think it's a mild assumption. Basically, you get strong connectivity if you make a graph containing these lambda STs. If that graph is strongly connected, then everything is reachable. Yeah. So ideally, so I can analyze this liquidity, right? But these are just formulas. It's not clear whether this liquidity is good or bad. I have this number 1 over 1 plus dV. Is it a good number or a bad number? Okay. So a node is bankrupt if nobody trusts them. And really, to say whether something is good or bad, we need to really be able to compare it to a centralized network. Okay. And so let's think of a centralized payment infrastructure. Yeah, I think here I'm assuming capacity C equal to 1 on each edge. The question is, yeah. So again, these results, so while the ideas are general, and I believe that they hold generally, to prove these very specific theorems, these very strong theorems, need to make these very specific assumptions. This very specific assumption, the degree, the node degree of each node is 1. So to analyze this, we really need to compare this network to a centralized payment infrastructure. Right? We can't just say, well, this is the bankruptcy probability is good or bad. It doesn't really mean anything. So how would you compare a credit network to a centralized payment infrastructure? And one way of doing it is to take any credit network and convert this into a centralized payment structure by introducing something like the Federal Reserve. Yeah? And I'm going to do a very permissive reduction. I'm going to say, I'm going to sum up all the trust that anyone has placed into one person. So let's sum up all the trust that anyone has placed into Asterix. In this particular case, that turns out to be 107. 7 from the Bard and 100 from Obelix. Okay. And I'm going to establish a trust of 107 from the Federal Reserve to Asterix. So I'm going to say whatever amount that anyone trusts you for, I'm going to give you that many dollars. Okay. And of course, I'm going to add reverse edges of infinite because everyone trusts the Federal Reserve. And this is going to be my centralized network. I'm going to compare the initial credit network to this new centralized network, okay, in terms of liquidity. Okay. Now, because this new centralized network is also a credit network, I can use basically the same math that I developed before to analyze it. The infinite edges actually make this analysis simpler because they reduce the number of kind of cycles you have to consider. So to convert this to a centralized model, for all, we introduce a new centralized node which I'm calling R for root, and I'm going to say the credit from R to the root is the summation of the credit that anybody was giving to you in the original network. The total credit in the system is conserved during conversion, and a slight variant of the liquidity analysis gives a steady state distribution and success probabilities. And so, and then we can do this comparison. And so for general graphs, the bankruptcy probability for a credit network is 1 over dV plus 1, where V is the degree of node V, and for a centralized system is 1 over D average, the average degree. So they're actually quite close to each other. It's just like the harmonic mean versus 1 over the arithmetic mean. Okay. The transaction failure probability, which is between two nodes, not the bankruptcy probability, but which is that a node is completely bankrupt, but that a specific transaction fails. For a star network is 1 over C in both systems. By both systems, I mean like we take the credit network and find the failure probability, then translate the credit network into a centralized system, and then analyze the failure probability. For a complete graph is the same, for Bernoulli random graphs is the same, and for a large class of networks, we can essentially show that the credit network and the centralized network have the same failure probability. We can also do it essentially for any expander. For any expander, we can show that the bankruptcy probability, that the transaction failure probabilities are the same in the credit network and the centralized network. So which means that if you're writing a credit network and the credit network expands, what that means is if you take any set of nodes, the total amount of credit that they issue to nodes outside them is much larger than the size of that set. So if you take a set of 100 nodes, the total amount of credit that they issue, the total amount of trust between them and everybody else is much more than 100. That's an expander. So as long as you have an expander, the centralized network and the credit network have roughly the same liquidity. So what that means is in a system like Stellar or and if we're doing some kind of a peer-to-peer payment system, as long as you have an expansion, you'll almost never run out of liquidity. So you'll almost never have to clear these transactions in real cash. You can always rely on this virtual currency. Yeah. So the question is, do all these statements require symmetry assumptions? I think so. The formal assumption is a little bit weaker. It's sort of more like that. So I think it's enough to assume. Sorry. So the theorems, yes. So there's what I can prove and what I can believe. So in terms of what I can prove formally, yes, they all require symmetry. What I believe is that what's actually enough is to assume that if you look at the transaction rate matrix, is connected and doubly stochastic. So doubly stochastic transaction rate matrix will essentially mean that the rate at which someone is buying something is the rate at which they are selling something, okay, and is connected. So I believe that these things should really I believe that all these results are true for doubly stochastic transaction matrices. And we have done simulation and it seems to be correct. And so if someone is looking for a technical open problem, in my mind, that's like a technical open problem, which is very interesting right there. Can you prove it for doubly stochastic transaction rates? That's what I believe, but the formal results are true only for symmetric. Oh, this is a positive, sorry, the question is this a positive result or a negative result? No, this is a very hugely positive result. Because it says that you have this credit network, we can only transact with your friends. Okay? And somehow, even if you are a centralized network, it won't really give you more liquidity. So there might be many reasons not to use a distributed currency like the one that I described, but liquidity is not one of them. You might have other reasons, like saying, why should I trust this random guy? I don't trust anybody. Or it might be, so it might be that maybe here you have to still trust a centralized broker to clear your transactions. Maybe there's no trusted centralized broker. Second, I think that with these dollars, you get a lot of anonymity. I can like take this dollar or this rupee and go pay for tea and nobody sort of knows who paid who. But here, these transactions are being cleared across a network. So someone in the middle of the network, just by looking at how their trust values change, might be able to infer that you bought something from you. Because I know I am both your friends and my trust in you went down and my trust in him went up. Maybe you bought something from him. So there might be lots of reasons for not using a system like this, but liquidity is not one of them. So that's basically the argument here. Yes. The centralized system only has to maintain the latest state of the trust network. You don't have to remember any history. But as a participant, if I can observe my own trust values, because I can keep track of my own history, I might be able to infer a transaction that happened. So the question is that is the ledger centralized and maintained? So maybe that's an orthogonal issue. So the system needs all you need is a state of the system, whether that's maintained by a centralized trusted authority or whether it's maintained by a distributed ledger is sort of an orthogonal issue. Like in Stellar, which is the example that I gave, there's definitely a distributed ledger, which is maintained in a cryptocurrency. So there's another orthogonal issue that we didn't talk about, which is who decides these prices. Like if I want coffee from you, how do I know whether to pay $1 or not? And so this is just a currency system. So a currency system is just a way of exchanging worth. It's not a way for setting prices. So again, it's not solving everything. This is not a system for this is not a market in the sense that I don't have supply and demand where I'm setting prices for goods. Okay? It's just doing one thing, which is doing this currency transactions. And there's only one narrow result, which is this liquidity is as good as a centralized system. So here are some open problems. One open problem was already sort of pointed out. I didn't mention it, so I'm glad someone pointed it out, which is to generalize the transaction model. Okay? But here's a surprising problem. Okay? So it's a theory problem. I'm sorry, the spacing is a little bit off. So theory problem is, imagine that like G, V, comma E is the underlying undirected multigraph of the credit network. So you take the credit network, you ignore directions, you get a multigraph. And you look at this multigraph. Then the way we prove some of these results on complete graphs and expanders that I alluded to, I didn't give the proof of, I gave the proof of that we have that every equivalence class is equally likely, or I more or less gave the proof. But I didn't tell you how I count those equivalence classes. And that happens via this reduction. The probability that a transaction from U to V succeeds in the credit network is the same as the probability that U and V are in the same connected component of a random forest of G. So forest of G is a subgraph of G where there are no cycles. A random forest is you pick a forest at random. And so probably the transaction from U to V succeeds in the credit network is the same as the probability that U and V are in the same connected component of a random forest of G. And that remotivates two classical open problems. These problems are sort of open, have been long open and beautiful, but I think they sort of didn't receive enough attention because there was no concrete motivation to study them again. So I think there's a new concrete motivation to study them again. And the open problems are, can I sample a random forest of G? So given a graph G, can you have an efficient method for generating a random forest of G, uniformly random forest of G? Okay. Because if you could, then you could estimate the probability that a transaction will succeed from U to V. So if I want to use simulation given an arbitrary credit network, if I want to find out the probability that U can transact with V, then I can generate a uniform forest many times and just measure this probability. But there's no known way currently of generating a uniformly random forest of G which is efficient or polynomial time. Okay? It sounds like a very surprising result, but it's because it's very easy to generate a uniform spanning tree of G, but it's very hard. Nobody knows how to generate a uniform forest of G. Then if you could prove that connectivity in a random forest of G is monotone, that would mean that success probabilities in a credit network are monotone. So what do I mean by that, by monotone? So imagine I'm given a graph G. Yeah, you add a new edge from, let's say you add a new edge in, there wasn't an edge between U and V and I add a new edge. Or maybe there was an edge and I increase one more, add one more edge because I'm allowed multi-graphs. If I add an edge from U to V for two arbitrary nodes W1 and W2, are they more likely now to be connected in a random forest of G or less likely? Now, it seems very bizarre that they would be less likely. Right? You added a new edge, so you increase the overall connectivity. Why would two other nodes W1 and W2 now become less likely to be connected in a random forest of G? But surprisingly, even though it seems so intuitively obvious, it's a long-standing open problem and no one has managed to prove it. Now, in our particular case, what that would mean is that if I were to increase the capacity on any edge in a credit network, I can only improve liquidity. Okay? So it seems like a very important result to prove, like a very basic result, and surprisingly, it's not known. So I think in terms of modeling, in my mind, the most interesting result is, can we axiomatize what a distributed currency should look like? Right? So once again, when you do regular computational algorithms, because the computational model is so well specified, we know there's a running time, there's a space requirement. That's very easy to do algorithms. When you do social algorithms, you have to constantly stop and say, well, I made this model, I hypothesized this network, it looks like a good network, but what is it good for? Is there like a fundamental reason to believe this is a good network? If I want to make a distributed currency system, what axiom should it satisfy? If I want to make a currency system, what axiom should it satisfy? So for example, I thought of liquidity, and this looks very good in liquidity, but maybe it's not good for anonymity, maybe it's not good for privacy. Can we axiomatize what a distributed currency system should look like, and either show that this is good or find something else that's good? And then connections to existing cryptocurrency networks. I think these are the interesting open problems. And surprisingly on time, so I have time for questions, yes.
When you talk about picking a random forest, do you mean of all the forests that you can construct, each of them has the same
Probability. Yes.
But if you just take a tree, for example,
Yeah.
right, then the only forest will be that tree. But if you add edges, you will probably get other forests.
Yes. No, sorry. If you take a tree, yeah. Okay. So I think.
Then the connectivity will go down for sure.
No. So I think so. The question is, if you have a tree, then the only forest is a tree, but that's not true. I think so. I think what you're alluding to is something very subtle, but if you take a tree, then this is also a forest of that tree. Yeah. There is no connectivity requirement. Yes. 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 So I'm not requiring that the thing is connected. And in fact, the reason I said what you alluded to is somewhat subtle is because, and the reason this problem is open, it might seem like it's an obvious open problem, and maybe we weren't smart. We were definitely not smart enough to solve it, but other people before us were also not smart enough to solve it. It's a long-standing open problem. One of the difficulty in this problem is related to something that you just alluded to. If I fix the number of components, then the monotonicity property goes away. So the monotonicity property goes away if I fix the number of components. If I for the sample thing, if I say I want to only sample random forests which have two connected components, or three connected components, and then four connected components, then the monotonicity property is not true. And so there's some. So it's like the difficulty. There's some difficulty there. It's not that the proof would have to be somewhat subtle, because this result sounds obviously true, but it also sounds obviously true that if I'm sampling if I restrict myself to having only one component or two components or three components one component of course is going to be connected. It seems obvious if I restrict myself to having four components and I add another edge, then the connectivity should only go up, but that's not true. There's a counter example which shows that's not true. So I think what you're asking somehow relates to the difficulty of this problem.
Is it known if you just take a tree
Yeah.
As n, n nodes.
Yeah.
Is it known how this probability scales? Because that should be very because there are lots of small points
Yeah.
that you can build, right?
So the question is, can we do this for a tree? So if G is a tree, then you can analyze it. If G is a tree and you just add one edge to a tree, then this is true.
Even if you don't, and I'm just saying because you're saying the probability is the same as that it's in the same component as it.
Yeah.
Does it then go down very quickly as n goes?
Also the question, so if you sample a random forest of G, what's the probability there's going to be a tree? Is that the question?
Take a tree,
Yeah.
you make a random forest like this,
Yeah.
and as a function of n,
Yeah.
my guess is that this probability goes down very quickly to 0.
So the question is,
Many forests,
yeah.
right, that has speed up, right?
Yeah. So the question is this probability going to go down to 0 very quickly as n increases? Yes. Because for a tree, we can explicitly analyze this probability. Because of the connection between random forest and success probabilities, if I assume the capacities are 1, then basically something which is a distance d away is only connected with probability 2 to the power minus d. So it's not, but again, the monotonicity here is not with n, it's with the same fixed graph you're adding another edge. Yeah. But for a tree, you can analyze everything. So once again, I think to belabor a point that I've made before, I think social algorithms are very interesting. They're also, for me, a little bit hard because it's not always, it's obvious that these problems are important, but it's not always obvious what the important parts of this problem are. And so somehow modeling, even though it seems like, I mean, the theory problems are interesting, but to me, this modeling problem is also at least equally interesting, which is, can we somehow axiomatize what these things are? And to repeat myself from yesterday, I think the reason it's important that people like us should do it is because if we don't do it, then these things are happening in industry anyway. And they'll either get them wrong or they'll get them right. And then as an academic community, we find ourselves in the position of criticizing them after the fact, as opposed to offering affirmative guidance in advance. And so they might ignore us, and industry might ignore us, but at least we should be able to say something to be ignored. Like we should have like, this is the right thing to do, and they may or may not believe us. Yeah. Thank you.